Greetings, detectives. Mrs. McKay here, and it's time to work on Clue 6. Clue 6 is going to be about the symmetry and diagonals of polygons. And I'm just going to warn you in advance that I'm going to try really hard to condense 3 major lessons into one. So I'm going to work really hard at being brief, but also this is a warning. Let's go ahead and get started. I can identify, our learning target clue is I can identify the rotational. Let's go ahead and write rotational, symmetry, the lines of symmetry, and the diagonals of regular polygons. Okay? I can identify the rotational symmetry, lines of symmetry, and diagonals of regular polygons. All right, let's go ahead and get started. Let's start with a little review. First of all, what is a polygon? Why don't you take a minute and just tell me what you think a polygon is? I don't need you to look it up. I just want you to, from whatever you know about polygons, tell me what you think a polygon is. Do that right now. Okay, here is what a polygon is. There's basically 3 main parts to a polygon. It is a closed figure, okay? It has straight sides, meaning there's no curves, straight sides, and every vertex connects to 2 sides, all right? So here would be a polygon, except that that's not a straight side. There's a polygon. Here's a polygon. Okay? Notice it has all straight sides. It's closed. Every vertex has 2 sides connected to it. Okay? So polygons can be concave or convex, but what we're going to be talking about mostly are regular polygons. But I wanted you to know those 3 things about a polygon. It's closed, it has straight sides, it's made up of line segments, and every vertex has 2 sides connected to it. Not 3, you're not going to see something that comes out like that. All right? Okay. The next thing that I want us to talk about are quadrilaterals. And I'd like you to tell me a little bit about what you know about quadrilaterals. First of all, what do you know about a parallelogram? What is a parallelogram? And if you don't know what these things are, then you should take a minute and go to the fact file, because that's one of the things that I said you needed to know before you started case 6. So if that's the case, stop the video, go to the fact file, and watch the video so that you know what these things are. All right, so tell me, what's a parallelogram? A parallelogram has 4 sides with 2 sets of parallel lines. These 2 are parallel lines, and these 2 are parallel lines. Parallelogram, okay? The other thing is that those 2 sides are equal, the 2 parallel sides are equal, and the other 2 parallel sides are equal, okay? A special subset of the parallelogram is a rectangle. Tell me, what makes a rectangle different from a parallelogram? Well, a rectangle also has 2 sets of parallel lines. It's a 4-sided figure with 2 sets of parallel lines, just like a parallelogram. So a rectangle is a parallelogram, but it's a special kind of parallelogram because all of its angles are 90-degree angles. Okay? Take a minute and tell me what you know about a square. What makes a square different from a rectangle? A square is a type of rectangle. It's a type of parallelogram. But what makes it different from a rectangle and a parallelogram? A square also has two sets of parallel lines. This one and this one. It's a four-sided figure with two sets of parallel lines. The difference, and it also has right angles like a rectangle. But the difference is that all of the sides are equal. It doesn't have two sets of equal sides. All of the sides are equal. Okay, so every side is equal. Tell me, what makes a rhombus unique? What is a rhombus? What makes a rhombus different from a square? Different from a rectangle? Different from a parallelogram? It is also a parallelogram. A rhombus is a parallelogram with two sets of parallel sides, but a parallelogram does not, and it's just like a square in that every side is equal, but it is not like a square because it does not have four right angles. These angles are different. So another way to look at, just like a parallelogram is sort of a pushed to the side rectangle, a square is a pushed to the side, a rhombus is a pushed to the side square. Sometimes we look at rhombuses and we see them as diamonds as well. Okay, so different ways, but a rhombus has four equal sides, but it does not have four equal angles, which are, it doesn't have four right angles. And the very last type of quadrilateral, which by the way, all of these are considered quadrilaterals because quad means four, so that means it's four-sided figures. And the last type of four-sided figure that I want to talk about is a trapezoid. Tell me what you know about a trapezoid. What do you know about a trapezoid? Well, a trapezoid is not a parallelogram, it is not a rectangle, it is not a square, it is not a rhombus. It is none of those because it does not have two sets of parallel lines. It only has one set of parallel lines. The top and the bottom are parallel, but it does not, and none of the sides have to be equal. Sometimes, usually these two will be equal, so I take that back. These two will be equal, but it does not have any right angles. It only has one set of parallel lines, and then the opposite sides are equal, but notice that they're not parallel. So these two are not parallel, but they're equal. These two are parallel, but these two are equal, but they're not parallel. These two are parallel, but they're not equal. So those are our quadrilaterals. And those are important because we're going to be looking at those, and we just need to know what they are, and we need to be able to talk about them intelligently. Now, according to our learning target clue, we're going to be able to identify three things related to regular polygons. And a regular polygon is a polygon that has equal sides. Okay, so a regular polygon is going to be a triangle that has equal lengths of its sides, an equilateral triangle. It's going to be a rhombus that has four equal sides. It's going to be a square that has four equal sides. Actually, I'll take it back on the rhombus. It's probably not going to be a rhombus because the other thing that makes a regular polygon regular is that all of its angles are equal as well. So in this triangle, we've got equal sides and then equal angles as well. okay, where here we do not have equal angles. Not all of them are equal. But in a square, we have 4 equal sides and 4 equal angles. In a pentagon, we have 5 equal sides, 5 equal angles. In a hexagon, 6 equal sides, 6 equal angles. In an octagon, we have 8 equal sides and 8 equal angles. And in a nonagon, we have 9 equal sides and 9 equal angles. So, but before we spend any more time with regular polygons, I want us to first talk about lines of symmetry. So the 3 things we'll be talking about are 1, lines of symmetry, 2, rotational symmetry, and 3, diagonals. All right? So let's start with lines of symmetry. Now, with a line of symmetry, that is going to be a line that reflects a figure onto itself. And there are many, many things in nature that have lines of symmetry. Usually, our face is pretty close to symmetrical. You can draw a line down the center of your face through your nose from top to bottom, and we've just created a line of symmetry. Whatever is on one side is a reflection across that line of symmetry of the other side. So a butterfly has a line of symmetry, right? So there's lots and lots of different things. Flowers often have lines of symmetry. Leaves have lines of symmetry. So if you can draw a line through a figure and what is on one side would allow you to reflect it on the other side exactly across the line of reflection, then you have something that is symmetrical, and that item has a line of symmetry. So what I'd like you to do is, there are some papers that I gave you that you should have that are copies of different types of polygons. And what I'd like you to do is, if you haven't already, I'd like you to cut them out and have them available so that you can try out a few things. Because one of the things that helps with figuring out lines of symmetry is if we can fold things. And since I can't fold it on this video, I want you to be able to do that a little bit. But what I can do is I can draw some lines of symmetry. So let's think about this triangle right here, this triangle, and see if we can find some lines of symmetry. So take your triangle, and if you need to pause the video, pause it and cut it out. Take your triangle and see if you can fold it along one line of symmetry. And I'm going to draw a line of symmetry. All right, so were you able to fold it along a line of symmetry like this? There is a line of symmetry right there, that pink line that I just drew, that basically divides my triangle into 2 equal parts, and notice that they are reflections, that each side is a reflection of the other side. If I look at this vertice right here, it is exactly the same distance from the line of reflection as the other vertice is. It's a direct reflection. So we spent a lot of time looking at reflections, and you can see that this triangle has reflected on itself. And you could take this line, fold along this line, and these two halves would match up directly. See if you can find another line of reflection. See if you can find another line of reflection. Well, you hopefully notice that you can draw another line of reflection right here. See that one? And there's a third one. See if you can find the third one. And as you may have guessed, it's right here. And so our triangle has 3 lines of reflection, doesn't it? Okay? Now, let's move on and take a look at our parallelogram. Tell me, can you find a line of reflection for this parallelogram? And if so, how many can you find? Look for it. Cut out the parallelogram, see if you can fold it, and if you can find a line of reflection. Now, you may have tried to fold it here, and you might think, oh yeah, it's divided in half, but it's not, is it? It's not an exact reflection, because look where this point is, right here. It's 1, 2 away from the line of reflection, but this point over here is not 2 away from the line of reflection. It's actually 3 away from the line of reflection. And then this one is 2 away, but this one is only 3. And remember that our line of reflection has to not only be the perpendicular bisector, has to be the bisector, but it also has to be the perpendicular bisector. So even if I wanted to make this be my line of reflection right here and divided my first half up here in half, my bottom half doesn't get divided in half. And if I tried to do it this way, said, well, there. Now it is. The only problem is that it's no longer a perpendicular bisector. It's not perpendicular anymore. It may be a bisector, but it's not perpendicular. So that does not have any, at least going that way, we don't have any lines of reflection. Now you may have said, well, what if I did it this way and I went across this way? Same issue. Even though I may have divided these in half, it is no longer, these are not perpendicular. It's not a perpendicular bisector. Okay, so let's try another one. Maybe you said that you want to try and do it diagonally from vertex to vertex, like from here to here. Maybe that does it. Except that as you look at it, you'll see that if I was going to take this point and I was going to draw my perpendicular bisector, then if I was going to make this straight, this would actually have to be over here somewhere. This point would have to come over here somewhere, and it's not going to. So the thing about a parallelogram is that it has no lines of reflection. Absolutely zero. All right? Now, let's take a look at our rhombus here, our rhombus. And tell me, how many lines of reflection do you see on this one? How many lines of symmetry are there? Well, hopefully you found that there are 2. 1 and 2. So 2 lines of reflection. Now, you might have thought, and you can always try this, try folding it, you might have thought that this one is also a line of reflection. But you'll find that when you try to fold it, you're not going to be able to get it to match perfectly. So try it. Try and fold it in half that way, and you'll find that you're not going to be able to get that to be a line of reflection or a line of symmetry. Now, take a look at our rectangle and tell me, how many lines of symmetry does our rectangle have? So our rectangle should have one that goes this way, right? So there's one. And then let's see, 1, 2, 3, 1, 2. Okay, so we got to go sort of halfway between, like this. And our rectangle has just 2. Again, the same issue. We're not going to be able to go corner to corner because you'll see that when we flip it, when we fold it along that corner, they're not going to match up perfectly. So 2 for the rectangle. Now, let's move on to our square. How many lines of reflection did you find on the square? Well, as you did it, you hopefully saw that you definitely can do the vertical line of reflection and the horizontal line of reflection. And now, with our square, we can actually do the diagonal lines of reflection as well, which I'm doing a terrible job of drawing, but you get the idea, right? Because really they should all connect perfectly right here in the middle. So our square has 4 lines of reflection. 1, 2, 3, 4. All right? Now let's go ahead and move on to the pentagon and see if you can find the lines of reflection for a pentagon. How many did you find? Well, there's 1. There's 2. There's 3. And 4. Did I get them all? 1, 2, 3, 4. I think I got them all. Okay, so 4 lines of reflection. Oops, no I didn't. There's 1 more. There's 5. So 5 lines of reflection. That makes a little bit more sense. Okay, so 5 lines of reflection. Now, I think what we'll go ahead and do is, while we're figuring all of these out, is we'll go ahead and start recording this in my little graph over here. So the number of sides, and this is for regular polygons, look it up here, noticing patterns on regular polygons. So if we have the number of sides, if we start with 3, we say that we have 3-sided figures, so a 3-sided, an equilateral triangle has 1, 2, 3 lines of symmetry. Okay? And then a square, which is our regular quadrilateral, 4 sides all equal, has 1, 2, 3, 4 lines of symmetry. So 4 sides, 4 lines of symmetry. And then our pentagon, our regular pentagon, had 5 sides and 5 lines of symmetry. So let's go ahead now and move on and figure out how many lines of symmetry our hexagon has. How many lines of symmetry do you think there are? Well, let's start counting. We got 1, 2, 3. So we've just connected our vertices. Notice when we had a 5-sided figure or a 3-sided figure, when we had an odd number of sides, we always connected a vertice to the opposite side, right? So this one went vertice to opposite side, vertice to opposite side, vertice to opposite side. On the pentagon, we went vertice to opposite side, vertice to opposite side, vertice to opposite side. You see how we always went to the opposite side? Now, let's continue and look at this hexagon. We went vertice to vertice vertice to vertice, vertice to vertice. That's 3. Are there any others that we can do? Are there any other lines of reflection? If there are, where are they? That's correct. Side to opposite side, side to opposite side, and side to opposite side. So we've got 6 lines of reflection. 6 sides, 6 lines of reflection. I hope you're seeing a pattern. The thing that's interesting, though, is that even though the lines of symmetry are the same as the number of sides, the reasons are different, right? Because basically, we have, with our triangle, we have the number of sides, but it's not a side to side, it's vertice to side. And then with our square, it's not a vertice to side, it's vertice to vertice and side to side. So it's just an interesting way of thinking about our different polygons. Okay, let's go ahead and do these last 2, and I think you can pretty much figure out how many there would be. So let's just go ahead and do that really quickly. This is an octagon, so we're going to go vertice to vertice, and we end up with 4. But then we also have side to side. And you get the idea. I'm just going to do this very fast. Okay? And then I'm going to let you go ahead and figure out how many, and why don't you go ahead and draw them in the all of the 9 let's see, we had an 8-sided 8 lines of rotation, lines of symmetry, and go ahead and draw in the lines of symmetry for this nonagon, a 9-sided. All right, so we know there's going to be 9. See if you can find them all. And I'm going to do it as well, but I'm going to pause it so that we don't use up our time. Okay, so I've just completed putting in the lines of symmetry for the nonagon, and that is lines of symmetry. So again, just as I asked you to do by trying the folding, that's our way that we can see that a line of symmetry is always going to allow the figure to reflect on itself. It's going to make equal halves, but it's not just equal halves, it's equal halves that are an exact reflection, a transformational geometry reflection across that line of symmetry. That line of symmetry is the line of reflection. Okay, so let's move on and talk a little bit about rotational symmetry. Rotational symmetry. Rotational symmetry is when a figure can be carried onto itself by a rotation. So what I want you to do is I want you to think about how we can take a figure and we can turn it, like find the center of that figure. So we've done that already. You can see, let me get my thing here. Like with my triangle here, where all those lines of symmetry intersect, that is a rotational point. So you could actually take your figure, your cutout triangle, you could hold it down at that center point, and you can turn your your triangle around so that you can bring one point around to the next point. And if it does, if you turn it, it will lay right back on top of itself. I'm going to try something really quick. Okay, I tried to do something that didn't really work, so we're not going to even do that. What you're going to have to do is you're going to have to do that rotation on your own. So what I want you to do is I want you to think about how many times you rotate this triangle around, how many different times you rotate it around. So you go from here to here, and then you can rotate it again from here to here, and then you rotate it again from here to here. So basically what we're looking at is we're looking at rotation angles. So you can rotate it 3 different times, and each time you rotate it, it looks exactly the same. Okay, it still lays on top of itself, and after the third one, it's back. If this was A right here, A would be back at the top, right? It would go, A would come down here, then A would come down here, then A would go around and be back at the top. So it takes 3 times to get all the way around. And the question is, what is our angle of rotation? How much are we rotating from here to here? Well, this is our measure of our angle right here. And this is the same measure, and that's the same measure. Now, you may not have remembered, but to go fully around a circle, it's 360 degrees, isn't it? So how many degrees is it to go a third of the way? You're right, it's 120 degrees. So this is 120, and then this is 120 degrees here. And this one's 120 degrees here. Okay, so the angles of rotation for a triangle are 120 degrees. Let's go ahead and talk a little bit about this parallelogram. Do you think it has any angles of rotation? Yeah, it does. When you turn it around, you'll end up with a parallelogram that looks just like this one, but you have to turn it a full 180 degrees, don't you? And so often this is called point rotation, and when it's just, or point symmetry, which just means that you have to turn it 180 degrees to get it to be a rotated amount. So we're not going to pay too much attention to those. The same is true for the rhombus and for the rectangle. All of them have point symmetry, not rotational symmetry, because you have to have less than 180 degrees for it to be considered true rotational symmetry. But let's look at our square and tell me, how many degrees do you think that we need to rotate it? Take a look at your square, and how many degrees do we need to rotate it to get this point, we'll say this is A, to here? "90 degrees. You're correct. This is 90 degrees. And this one from here to here to the next one would be another 90 degrees and another 90 degrees. And so it takes 4 90-degree angles to get the 360 degrees to get all the way around. So 4-sided regular polygons, which are squares, have, whoops, I wrote 360 and I really meant to write 90. 90 degrees. All right. Now let's take a look at our pentagon and tell me to get from this point to this point, okay, what is our angle of rotation going to be? Did you figure it out? Have you noticed a pattern yet? Well, if it takes 360 to get all the way around, then there are 5 rotations, 1, 2, 3, 4, 5. And when we take 360 and divide it by 5 even angles, what do we end up with? We end up with 72 degrees. Okay, let's do the next one. Here's our hexagon. That was point A. Here's point A, and to get point A to point B, I said this was 72. What is it to get here? Can you figure it out? Here's our angle. And how many do you think there are? You're right. There are 6. Oops. Ignore that one right there. Not that one. 1, 2, 3, 4, 5, 6. 6 angles, 360 degrees, must be 60-degree angles. All right, next one. Here's our center of rotation. Here's angle A. We want to get angle A. We want to get point A to point B. How many different rotations are there? Well, there are 8 sides, so there are 8 angles of rotation. And how do we figure out what each angle of rotation is? Well, we can divide 360 by 8, and we get, let's see, that becomes 32, 45 degrees. See what I'm doing? Go ahead and do the last one. Tell me the number of rotations required. 9. And each angle of rotation is how many? 40 degrees. Okay. Now, before I go any further, let's do a little bit of generalization. Generalization says that we look for a pattern and we say, can we generalize and say for the nth number of sides? Meaning, any number of sides, can we predict how many lines of symmetry and what the angle of rotation would be? So if we have a polygon that has n sides, how many lines of symmetry will that polygon have? That's correct. It will have n lines of symmetry. Here's my next question. How many angles of rotation will it have? That's correct. It will have n angles of rotation. Now, what is the degree of each angle of rotation? How will you figure that out? How will you figure out the degree, the amount of that in each angle of rotation? 360 degrees divided by n. Very nice. Okay, now it's time to move on to diagonals. Diagonals. And let's talk a little bit about what a diagonal is. A diagonal is any line segment that connects non-consecutive vertices. All right, well, let's identify what all of these words mean. Consecutive means right next to it, to another, okay? One right after another. So remember, the vertices are going to be our points. So here's a vertice, here's a vertice, here's a vertice, here's a vertice, okay? So a diagonal connects non-consecutive. So if this vertice is next to this vertice, vertice A and B are consecutive because they're right next to each other. So it can't be the side, all right? It can't be the side of the polygon because that's what consecutive vertices do. They're connected by the side. So let's go ahead and say that this is D and this one is C. Okay, so if we wanted to find our diagonals, we couldn't say AB is a diagonal, and we couldn't say AD is a diagonal, but we could say that AC is a diagonal. Now, a diagonal could be a line of symmetry, but it doesn't have to be, okay? Because notice that this diagonal is not a line of symmetry, okay? But it is connecting two vertices. And you can see that there's another diagonal right here, which is BC. Notice that my two lines of symmetry, which actually go from side to side, are not considered diagonals, okay? Take a look at our triangle and tell me how many diagonals are there on this triangle? How many diagonals? Ah, that was a trick question. You might have tried to look at these lines of symmetry that we had and figure and say, oh, well, there's 3 diagonals. But remember, a line of diagonal has to connect vertices. It has to connect the points. So that means A has to either connect to B or A has to connect to C. But the other thing is that it has to be non-consecutive, which means they can't be right next to each other. So there are no other vertices that A can connect to. So how many diagonals does a triangle have? It has 0. 0 diagonals. All right? Now let's look at our square. How many diagonals does a square have? It has 2. 2 diagonals for a 4-sided regular polygon. Tell me, how many diagonals does a pentagon have? This one's a little trickier. I've got 1, 2, okay? I've got 3, 4, and 5. Notice that my diagonals are not lines of symmetry. They are not lines of symmetry, okay? Like I said earlier, a diagonal might be a line of symmetry, like in our square, our two diagonals are lines of symmetry, but in our odd size or odd shaped, odd number sized regular polygons, because we're not going vertice to vertice for our lines of symmetry, we're not going to get our diagonals to be lines of symmetry because our diagonals have to connect vertice to vertice, right? So let's count them. 1, 2, 3, 4, 5. There are 5. Did I count them correctly? 1, 2, 3, 4, and then 5. Did I do that right? I think I did. Okay? Now, let's do the lines of symmetry, the diagonals for a hexagon. See if you can find them all. See if you can find them all. Well, I'm working on it, and I found 6 so far. I found 1, 2, 3, 4, 5, 6. And now I'm here. I think I already did that one, so I can't do that one again. Here's 7. 8. And let's see, I already did that one, 9. 9 vertices. Or sorry, 9 diagonals. Did I get them all? Each one should have 3 coming out of it. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. But I'm not going to count them twice, so I end up with 9. Now this one's going to take this one actually has a pattern, so I want you to see as we do this if you can find the pattern. Let's move on to our 8 octagon and see if we can find our so there's 1, 2, 3, 4, 5, and then that one and that one we wouldn't count. Okay. Can you predict how many there are? 6, 7, 8, 9, 10, and let's see, that one's already been done. 11, 12, 13, 14, 15, 16, 17, 17, 18, 19, 20. I think I got them all. 20 for our 8 sides. How many do you think there will be for the 9 sides? See if you can make a guess and then try to figure it out. Well, what did you come up with? Did you come up with 27? I went ahead and counted them all out. And I want to know if you've noticed any pattern as you drew these out. Did you notice a pattern? Can we predict how many diagonals there will be for an n-sided polygon? An n-sided polygon. Did you find a pattern? Tell me the pattern that you found. Now, if you didn't find the pattern, that's okay, because let's see if we can look for a pattern ourselves. Now, there's lots of different ways that we can do it, but I think the way that's going to be the easiest is if we look at a particular point. So let's start by looking at this point right here, this vertice. How many diagonals are coming out of this vertice? Let's count them. 1, 2, 3, 4, 5, 6. Okay? There are 6 vertices coming out of this particular, there are 6 diagonals coming out of this particular vertice. How many sides does this have? There's 9. Okay? There are 9 vertices, but there are only 6 diagonals for this one vertice. Well, that kind of makes sense because we wouldn't have a diagonal that goes just to this vertice, right? It has to go to another vertice. So we kind of have to take away the diagonal, or we have to take away, we can't say that there are 9 diagonals for this vertice because one of the 9 is the actual vertice, right? You can't have a diagonal that goes from one vertice to the same vertice. So we're going to take that one away. And then we also know that we can't have these 2 sides. So we're in essence eliminating this right here, that diagonal, and that diagonal because they're not diagonals, right? So then we have, what's left is we have 6 other vertices of the 9 that can make a diagonal. So for every vertice, we have 6 separate diagonals. 6 for each one, and you can count them and see that, right? So we've got 1, 2, 3, 4, 5, 6, and then we go to this one, we've got 1, 2, 3, 4, 5, 6, and for this one we go 1, 2, 3, 4, 5, 6. There's 6. For each vertice, there are 6 diagonals. Okay? So why not just say, okay, 6 vertices, 6 vertices, 6 diagonals times 9 vertices. 6 diagonals times 9 vertices, well, that would be 6 times 9 would be 54. But I don't have 54. When I counted them, I had 27. But do you see a pattern between 54 and 27? Maybe you do, maybe you don't. Let's take a look at this. Let's do the 5 right here. How many vertices are there? Well, there are 1, 2, 3, 4, 5. So there are 5 vertices, And how many diagonals come out of each vertice? Well, look, 1, 2. There are 2 that come out of each vertice. Well, that makes sense because if we have 5 vertices, we can't count a diagonal for the one that we're starting with, and we can't count the 2 sides, so we've got to take those 3 away. So what's left are 2. So 2 times 5 equals 10. So we have 2 diagonals for each of the 5 vertices, gives us 10 diagonals. But according to what we counted, we only had 5. Okay, well, let's look at the square. The square has 4 sides, 1, 2, or 4 vertices, 2, 3, 4. So we got 4 vertices, and each vertice only has 1. 1, 1, 1, 1. So 1 times 4 equals 4, but the total number of vertices is only 2. Do you see the pattern now? That's right, we're dividing by 2. And the reason we divide by 2 is because this vertice right here is the same vertice that we were counting for this one over here. So we have to divide the number of vertices in half because we would end up doubling up. Some vertices, when we count our vertices, we've got 4 vertices, but we really don't have 4 diagonals. Okay, we only have 2 diagonals because when we say one diagonal for this vertice and 1 diagonal for this vertice, well, when we get down to this one where we say 1 diagonal for this vertice, well, we've already counted it, haven't we? And when we say 1 diagonal for this one, we already counted it. So we have to divide everything in half. So our little formula is going to be the number of vertices minus 3. Remember, because we said 5 vertices, but only 2 come out, so 5 minus 3 is 2. We said 9 vertices, but there's only 6 diagonals, because 9 minus 3 is 6. Okay, because we don't count the vertice that we're looking at, and we don't count the ones on either side. Okay, so 9 minus 3, that tells us how many diagonals there are. And then we multiplied that by the number of vertices, so n minus 3 times n, but then we had all these duplicates, so we had to divide by 2. And we can now predict the number of diagonals for any sided polygon. All right, I don't know how long that took, probably longer than you wanted, but we now have covered lines of symmetry, rotational symmetry, and diagonals. Go ahead and write yourself a key idea, and I will see you in class.